Continuing the example from the first video, we verified that we could use L'Hopital's rule. So I took the derivative of the numerator and I took the derivative of the denominator. So here the derivative of e to the 3x is e to the 3x. Using the chain rule, we then have to multiply by 3. So we get 9 e to the 3x. In the denominator, we have that same expression, so we get that same derivative, and then the derivative of 5 is 0. So here's where we are at in our limit, and you might notice that the numerator and denominator are equal, and so they do just reduce down to 1, and the limit of a constant as it approaches any value is always just that constant. And that's always the goal of L'Hopital's rule, is to be able to evaluate the limit in order to get a constant answer, and that's what we've got. All right, let's look at another example in that same indeterminate form. Here we're going to be taking the limit as x approaches infinity of the rational expression natural log 3x plus 5 divided by the natural log of 7x plus 3 and then plus 1 on the outside in the denominator. So let's see the indeterminate form that we have when we use direct substitution to try to evaluate this limit. So we're going to get the natural log of 3 times infinity plus 5, which is the natural log of infinity, over the natural log of 7 times infinity plus 3, so just infinity plus 1. And again, we can't really plug infinity into a function to evaluate it, but we want to see what it's approaching. And as the x values of a natural log function head towards infinity, the y values also head towards infinity. So on the top we get infinity. On the bottom, the limit as the natural log function approaches infinity is also infinity there, and then if you add 1 to infinity, you still have infinity. So this is the indeterminate form that we have when we try to use direct substitution to evaluate this limit. So we're going to use L'Hopital's rule in order to continue. So I'm going to take the derivative of the top and the derivative of the bottom, and I'm going to do that separately. The derivative of a natural log function is always 1 over the argument multiplied by the derivative of that argument. Same process on the bottom, taking the derivative of the natural log function. 1 over the argument times the derivative of the argument, and then the derivative of 1 is 0. So before I use direct substitution to evaluate this, I'm just going to rewrite it, clean it up a little bit. So I can write the 3 on the top of this fraction and the 7 on the top of this fraction. And whenever we have two fractions divided by each other, we can use the copy.flip process where we multiply by the reciprocal. I'm sorry, we multiply by the reciprocal. I said that correctly. So we'll take the first fraction, 3 over 3x plus 5, and we'll multiply it by the reciprocal of the bottom fraction, 7x plus 3 over 7. And if we multiply those two fractions together, we'll have 21x plus 9 over 21x plus 35. Let's use direct substitution now that we've cleaned it up. Okay, so we're plugging infinity into this function, or we're evaluating it as x approaches infinity. So on the top, 21 times infinity plus 9 is still infinity. And then on the bottom, 21 times infinity plus 35 is also still infinity. So once again, we have another L'Hopital form. and we have to repeat the process. So once again, I'm going to take the derivative of the top, and I'm going to take the derivative of the bottom. Derivatives are easier here because they're both linear functions. So the derivative of 21x plus 9 is 21, and the derivative of the bottom is also 21, and therefore I have the limit as x approaches infinity of a reduced constant of 1, giving me a final limit of 1. Alright, so we looked at two limits where we had 0 over 0 L'Hopital form, and then we looked at two limits where we had infinity over infinity L'Hopital form. We're going to move on and look at some things that get even more complicated. So let's take a look at what happens when we have the indeterminate form of 0 times infinity. Alright, so let me show you an example of 0 times infinity. Let's say we're trying to find the limit as x approaches 0 of x times the cosecant of x. So, using direct substitution here, we get the limit as x approaches 0 of 0, if I plug 0 in for x, I get 0, times the cosecant of x. And remember, the cosecant is 1 over sine. So if we do 1 over the sine of 0, we're doing 1 over 0, and that's infinity. So this is not a L'Hopital form. It is an indeterminate form. It's something that we can't calculate on a calculator, 0 times infinity, but it's not a L'Hopital form. So the strategy for 0 times infinity, when we have that form, the strategy, in order to be able to use L'Hopitals, is to rewrite this as 0 over 0 or as infinity over infinity in order to use L'Hopital's rule. So think about ways that you can take something in the form of 0 times infinity and write it as 0 over 0 or infinity over infinity. And I'm actually going to take the zeros and the infinities out of it for a moment, and I want you to think about a way to rewrite 3 times 4 as a division. Okay, so I've got two things that are being multiplied, and I want them in a form where they're being divided. So instead of taking 3 times 4, I can take 3 and divide it by 1/4. And those mean the same thing. That in either way, they're both equal to 12. So the strategy that we're going to use here in order to rewrite this as a L'Hopital form is to divide by the reciprocal of one of the functions. So we're going to be dividing by the reciprocal of one of the functions. Dividing by the reciprocal is the exact same thing as multiplying, which is what we have. So let's go back to the example. Limit as x approaches 0 of x times the cosecant of x. So again, we're going to rewrite it in a L'Hopital form. So we can say that the limit as x approaches 0 of x divided by the reciprocal. So the reciprocal of cosecant is just sine. Okay, cosecant is 1 over sine, so its reciprocal is regular sine. So I'm going to take this x, and instead of multiplying it by the cosecant, I'm going to divide it by the reciprocal, which is sine. Now, let's try to evaluate the limit. So if I were to use direct substitution, let's see what we would have, what form we would have. We'd have 0 on the top. We'd have the sine of 0 on the bottom, which is 0. Now I've rewritten it so it's in a L'Hopital form, and now I can go ahead and use that rule. So I'm going to take the derivative of the top, and I'm going to take the derivative of the bottom, and I'm going to do it one at a time. So it has to be in this form in order to do that. The derivative of x is 1. The derivative of the sine of x is cosine of x. So let's now try direct substitution and see if that will give us a constant. Nothing to substitute on the top. On the bottom we have the cosine of 0. The cosine of 0 is 1. So my final limit is 1.